I welcome you guys to another lesson session on finite element procedure. In today's lesson, I would like to show you how to solve this problem, this one-dimensional problem, and using the ANSYS program. In my previous lesson, I solved this problem using hand calculation and also using the finite element procedure on MATLAB program. This problem is a one-dimensional problem, and it consists of two material parts, material part 1 and material part 2. And we have boundary condition at the end of the structural body at node 1 and at node 3. And we also have a point load at the intersection of the two parts, that is at node 2. At node 2, the point load is 160 kilonewton. Element 1 is 90 mm long, element 2 is 20 mm long. We see the cross-sectional area and the Young modulus of element 1 here, and the cross-sectional area and Young modulus of element 2 here. So we are asked in this question to determine the deformation, that is displacement quantity at node 2, at this point, at node 2. And we are also asked to calculate the stresses in each element, the stress in element 1 and the stress in element 2. So now we are going to move to the ANSYS and working environment to solve this problem. To open the ANSYS Workbench, you can quickly type Workbench in your Windows search. So I'm using Workbench 2021 Auto. So I've clicked on it. This might take some time to load, say like 1 to 2 minutes. Now we are in the ANSYS Workbench work environment. We need to drop the static structural solver. We need to select and drop the static structural solver from the left-hand side of the screen to the middle of the screen, as you see on the screen. So we can name this solver, say one-dimensional problem. Anything you want to name it, you can give it a name. So what we need to do, we need to go through this workflow from the engineering data to the geometry to the model to the setup to the solution to results. In the engineering data, this is where we enter our material property for our finite elements, like the Young modulus. Let me go back to my PowerPoint presentation. In our statement problem, we're given that the Young modulus of material 1 is 200 megapascal, and the Young modulus of material 2 is also 200 megapascal. So we need to define one engineering material because we only have one Young modulus. Assuming we have two different Young modulus, we are going to define two material properties in the ANSYS engineering data interface. Let me go back to the ANSYS Workbench work environment now. So what I need to do now to define my engineering material, I need to double click on the engineering data. So I double click on it, and I need to create a new material. And that new material, we need to give it a name at this section of this interface, the outline of schematic. So I'll give it a name. I'll call my new material steel. Can be any name you choose to give it. I'll call it steel because the Young modulus, which is 200 Pascal, is similar to the Young modulus of steel. So I'll name my new material steel. And in the new material, Currently, the new material doesn't have any property assigned to it. So, but we can add property to it by dragging and dropping any of the property on the left-hand side of the screen here on it. So I'm going to click on isotropic elasticity, and I'll drop it on my new material created. So once I do that, you will see this table below here populated, and in this table I need to define my Young modulus and position ratio. From the question, we know that our Young modulus is 20 gigapascal, so I want to enter 20 gigapascal as the Young modulus of our new material, but first I need to change the units to gigapascal. You see, ANSYS is a very powerful software. You can enter your value in different units. So I will choose gigapascal and I will enter 200. I'll do the same thing for the position ratio. Although in the question we're not given parameter for the position ratio, you can enter any value here. Like you can enter typical value of position ratio. This parameter will not affect your results. It is like this because ANSYS is not actually built for one-dimensional problem. For one-dimensional problem, we don't actually need portion ratio to analyze finite element problem. But because ANSYS is built for 2D and 3D structural 2D structural problem, and that's why the portion ratio needs to be specified. For every new material created in the static structure, you need to define at least two parameters, which is the portion ratio and the Young modulus. If I don't define these two parameters, I won't be able to perform any analysis on the software. So I'll give the portion ratio, I'll enter a value of 0.3 and press enter. So this is what we need to do in this engineering data interface. We specify the Young modulus and portion ratio. Now I'll close the engineering data. So now we have defined our material data. I'll move to the next workflow, the geometry. But I want to draw your attention to, when you move to the geometry, you will see this table shown on the right hand side of the screen. As I showed you in my last video, under this ANSYS type, you see under this analysis type, you see 3D and 2D. You don't see one dimension. It tells you that ANSYS is not actually built to analyze one-dimensional problem, but we can trick or force the program to analyze our one-dimensional problem. So I will leave this analysis type, I'll leave it at 3D, but actually I'm going to reduce this 3D to a 1D analysis type. I will show you how this is done in this video. I need to check on this number 12 rule, the line body. I want the line bodies active because my finite element in ANSYS program is the line bodies. So I check the line bodies. Now go back to the geometry workflow, and either you double click on it or you right click. I right click. Once I right click, this is shown. I can draw my geometry. I want to define my geometry, my geometry data. I can define this geometry data either in the SpaceClaim drawing environment or the design modular drawing environment. But in this tutorial, I am using the SpaceClaim geometry, the geometry 3D drawing environment. So I'll click on new SpaceClaim geometry. This takes some time for the SpaceClaim geometry window to come up. The Workbench is trying to start the SpaceClaim working environment. So it takes some time for the window to come up. Say like 1 minute, we need to wait for 1 minute. Oh, I think the SpaceClaim window has opened. I think this is it here. So I'll click on it. So this is SpaceClaim window environment. So this is a 3D working drawing environment. I would like to draw on a plane. So I want to convert this 3D drawing environment to a plane, to a 2D plane drawing environment. So to do that, you click on this button here, select new sketch plane. So I can select either the XY plane or or the YZ plane or the XZ plane. You see this as I'm moving the cursor. So you can choose any of the three. So I choose the XY plane. To choose the XY plane, you need, once you are at that plane, just left click your mouse and the plane gets selected. You can bring the plane, this XY plane to view by clicking this button here. So I've clicked on it. We need to go back to the PowerPoint so to know the dimension of our two material. The dimension of the first material is actually 90 mm. The second one is 120 mm. But I would like to show you on PowerPoint. I would like us to note these four variable dimension. The length of material 1 is 90 mm. The length of material 2 is 120 mm. The cross-sectional area of material 1 is 50 mm square, and the cross-sectional area of material 2 is 100 mm square. So please note this dimension. So I'll move back to my SpaceClaim working environment now. So in the SpaceClaim working environment, the first thing we need to do, we need to sketch our two material parts using the line command under the create panel here. So I'll click on the line command. So, and I want to start my sketch from the 0, coordinates, the XY coordinate 0, 0. So I put my mouse is on the 0, coordinates now. So I click on it and I enter the dimension of the length of this line as 90 mm. I zoom in and zoom out. I draw the second part, 120 mm, and press enter. I press escape to leave the line command, and I also click on the end sketch editing button here to leave the sketch command. So now that we have defined the length of our two elements, we need to define the cross-sectional area. And to do that, we need to go to a tab called at the top here, called the Prepare tab. Click on the Prepare tab. Under the beam panel, click on Profile. We're using a rectangular section. And as I showed you earlier, we need to actually create two sections. We have 50 mm square for as the cross-sectional area of element 1 and 100 mm square for this cross-sectional area of element 2. I've created one section here. You can see a rectangle. The section is called rectangle. I need to create another one. So I will come back here and I will also click on this rectangle button again to create a new rectangular section. A new section is created called rectangular 2. I can edit the name, give it any name, but let's leave it as it is. But we need to edit the dimension of the rectangle because we need to edit the dimension of the rectangle to fit the statement problem. So I click on rectangle and I right click on it and click on edit beam profile. Oh. Here we can change the length and width of this rectangle using from this dimension parameter stated here, the B and the H. The B and the H. Currently the B is 10 mm and the H is 10 mm. You can also see it here. B is 10 mm, H is 10 mm. For the material 1, which is 50 mm square, Assume the cross-sectional area we're using is a square. So our length, our B and H should be square root of 50. So let's use the calculator to calculate the square root of 50. So this is 7.071067. I'm going to copy this value and I will paste it at this position. I'll press enter. I'll do the same thing for H. Paste, enter. So you see the B dimension is now 7.07 mm. The H dimension is 7.07 mm. So now you can close this cross-sectional window. The cross-sectional window is denoted by this tab here, X, Y, X. I can close it. Click on the structure tab, structure button here, and you also need to change the dimension of the dimension of the cross section for rectangle 2. So I'll click on it. Right click, edit beam property. Our area cross section for material 2 is 100 mm square. So if we are assuming a square cross section, our length and width will be 10 mm. And luckily our length and width is already 10 mm for both B and H, so we don't need to make any edit here. So I'm going to close this cross-section window and go back to the structure button. Now we need to apply this cross-section to our line element. So you select one of the cross-section. I'm selecting the rectangle cross-section, and you click on create, and you select material 1. So I'm applying rectangle. No, should be rectangle. Also make sure that this is on rectangle here. So choose rectangle profile here and select the 90 mm line body which we drew. So the rectangle cross section which is 50 mm square is applied to this element, and you will see this from here. You see a new folder created called beams, and if you should check the interior, you see in a beam element has been created. Also change the profile to rectangle 2 and apply to the second line body, and the second beam element is created. Now we have two structural beam elements. So what you need to do, you press escape on your keyboard to leave the create command, and let's check the property of the structural beam element that was created. So I'll select the first beam element. So the first beam element, the profile that was attached to it, we see is the rectangle profile. We need to change the structural element type from beam to truss elements. So you do this by changing the beam type here from here to link stroke truss element. So you also do this for the second structural element. Change the beam type to link stroke truss element. So now we have reduced the problem from a 3D structural element to a 2D analysis type by changing the type here to link truss type. What we need to do before we leave this SpaceClaim working environment, we need to click on this design button here, and we need to under this we need to select share under shared topology. Currently it is at none. We need to select share. It is very important. We won't be able to run analysis if we don't, we won't be able to run analysis and get results if we don't apply this setting. So make sure under the shared topology, this is set to share. Now we can leave the SpaceClaim work environment um, by closing this window. Now we have defined our geometric property, and we have also defined our material property. Now we need to move to the next workflow, the model workflow. So I will double click on it to open the window. The window under the model workflow is called the mechanical window. You can see here, under here it's right starting mechanical window. So it will take, it's actually fast, it came on quickly. So this is the mechanical window where we define our finite element, we define our boundary condition, we define our applied load, we run analysis, and we also, this is where we get our results, our color plot results. So this is the mechanical window, and in this interface, we need to walk through this workflow from the model to geometry to material to cross-section. You need to define all this. So I will start from the first one, the geometry. Now the geometry, that's where you will see the geometry which you define in the SpaceClaim work environment. You see the two structural elements which we created in the space claim working environment. You see it here. So you see we have the truss elements where we applied our rectangle cross section, and the other truss element where we apply rectangle 2 cross profile. So these are our two structural elements in the model. It's denoted by these two lines. So what we need to do here, we need to apply our material property to this structural element, to these two structural elements. So I'll select the first structural element, and I need to assign the steel property which I created in the engineering data to it. So under material assignment, right click on it, you set it to steel. It has been changed to steel. You do the same thing for the second element. Change the material property to steel. You move to the under the material. You don't need to actually do anything here. What this just contains the list of materials which is available for you to select to apply to your structural element. So in this model, we have steel and structural steel. This structural steel is always available by default. This steel is the material we created in the engineering data. Under the cross section, we see the list of the two cross profile which we created in the SpaceClaim working environment. Under the coordinates, this model just has only one coordinate. There's a coordinate here, x, y, z coordinate. We can create new coordinates if we like to suit our needs. Say you need to use it for something, you can create new coordinate, but I don't need to create new coordinates. So I'll move to the next workflows. Under this connection, here you don't need to do anything for this question. It's already checked with a green tick. So we jump it. But this connection is a very important part of finite element analysis. It defines how two materials, how they interact together at contact. Say you have a reinforced concrete. We have concrete and reinforcement. So you will need to define the interaction between the reinforcement and the concrete. If you are working with reinforced concrete material, you need to define the connection parameter here. So this is a very important part of the ANSYS program. But for this question, we don't need to do anything under this step. So move to the mesh. And under the mesh, I would like to change the element size to 120 because 120 mm is my greater dimension. I have 90 mm and I have 120 mm. And I want to force the ANSYS program to just match two finite elements. So that's why I'm giving it 120 mm element size. Under the element control, we have linear and quadratic. I'll choose linear because that's what we use one-dimensional linear element in our finite element procedure on MATLAB. So I would like to see the results. I would like to analyze this problem using using the linear finite elements. So these are what you need to specify under the mesh for this question. So I'll move to the static structure. This is where we define our boundary condition and our loads on the structural body. So what you need to do here, you need to right click, go to insert, select displacement support. So displacement support, this displacement support is applied to this element. Why was it applied to this element? Because when I selected the displacement support, I also selected this element. So the support gets up. The support is applied to this element, but I can change that. What I need to do, I need to select the node where I want to apply this support. So I'll use the vertex selection tool here. I'll select this node 1, and I'll click on apply. So I've changed the application of the displacement support from the element selection to the node selection. So the displacement support now is applied to our first node here at where you see this yellow shape. So in the under this support, and we also need to define the restraint at that support. I drew this element in the XY place. So, and currently our analysis is a 2D analysis type because I chose the link source element type. So I need only to define the X and Y restraint for this question. I'll leave the Z restraint as free. So for the X component, I will enter 0. For the Y component, I will enter 0. I need to also, so this is this support at node 1. I need to create another support at node 3 because we have two boundary conditions at node 1 and at node 3. So what you can do, you can duplicate this displacement support. So I'm going to duplicate it. So this is different. This is another way of creating support in this working environment. So I'll click on duplicate, and I need to reapply this new support to node 3. So I'll click on node 3 and I will apply. I'll click on apply here to apply the support at node 3. So the displacement support tool has been applied to node 3, and the X and Y component is already set to 0. So, and these are the restraints I actually want at node 3. So I'm not going to do anything here further. In the question, let me go back to the PowerPoint. We have 160 kilonewton at node 2 pointing to the left. So I'm going to define that load at node 2. Click on static structure, right click, insert, click on force. Select the node where you want to apply the force. So I'm selecting node 2 and I will click on geometry. So this red shape denotes the load at node 2. The define by type, I'll change it from vector to component. And I want a force applied in the X direction, 160 kilonewton. This is my X direction. So my X direction, my element is along the X direction. So I want to specify 160 kilonewton in the X direction. The unit type here is in Newton, so you should be careful to enter the right value of your force. So I'm going to enter minus 160,000 Newton because the force is pointing to the left. So I've specified the force at this point. So we can run our analysis, but if you should run your analysis now, you will get an error message because the analysis type is currently a 2D dimension type. We need to reduce it to a one dimension type. Our node 2 can move in the y direction. There is any restraint there. Our node 2 can move both in the x and y direction. So we need to restrain the y component so that the node can only move in the x direction. So restraining our node in the y direction at node 2 changes this problem to a one-dimensional type. So I'm going to create a new support. Click on static structure, insert new displacement support, apply, select node 2, click on apply. The y component, set it to 0. So I've restrained movement at node 2 to 0. Now we can run our analysis. I'll click on solve to run analysis. Is there a problem? Not enough constraint appear to be applied. It's taking. Let's see what happens. I'm sure we are not going to have any problem because I've done this before. So we see under the solution, we see the green check, meaning we don't have any problem. So we can show our result. We need to tell ANSYS what the result we want to see. And to do this, you have to add it in under the solution tree. So say you want to find out the reaction at the support. You have to add it from the solution tree. Say you want to find the stress in the element, you have to add it from the solution tree. Say you want to find the deformation in the x direction, you have to add it in the solution tree. So under the solution tree, you right click, insert deformation directional. So deformation in the x direction is already set to the x direction, so I don't need to do anything here. If I was looking for deformation in the y direction, we change to y direction, but I'm actually looking for deformation in x direction, so I'll leave it at x direction. On the solution, you right click, easier force, beam result, easier force. So here this results will show us the easier force in both finite elements. We don't need to do anything under the details of easier force table. For our reaction, we use we'll go to probe force reaction. Under the force reaction, you need to define the boundary condition. So the boundary condition that actually the support which we've created. The support at node 1 is it's called displacement. So I will select displacement. Like this displacement support is what is applied at 1. So I want to find the force reaction at the displacement boundary condition. So that's why I selected boundary condition here. I will duplicate this force reaction result. I'll duplicate it. So under force reaction result is created, but this I will apply it to I will apply it to displacement 2, to boundary condition displacement 2, because this displacement 2 is the support applied at node 3. I know this. So you can see force reaction at node 2. Displacement 2 support is applied at node 3. So that's why I chose at the boundary condition for force reaction 2 to be displacement 2. So now we can run analysis to check these 4 results: direction, deformation, area force, force reaction 1, force reaction 2. So I'll click on solve. So the deformation, this is the deformation diagram. You can see at the end, This legend states that the red means zero displacement. So at the end, we have zero displacement. At the intersection of the two elements, which is blue, we have minus 0.576 deformation. And this is actually what we got in our hand calculation. Let me show you on PowerPoint. In my previous lesson, we got the deformation to be 0.576 shown here. Sorry, 0.576. You can invert, say you don't like this color display, you can invert it. Right click on this color legend, color scheme, reverse rainbow. So the blue is now denoting zero displacement, the red is denoting minus 0.576 mm. To probe your deformation value, you can click on probe here and snap at zero. At the beginning, we have zero displacement. At the intersection, we have minus 0.576 mm deformation. At the end, we have zero displacement. At the intermediate position, you can also get deformation value, but I need to turn off my snap. I need to uncheck this snap button here. See somewhere here, we have minus 0.29819. Somewhere here, we have minus 0.28294. Say you want to see how the object deforms, like you want to see an animation, you can click this play button. So you can see how the 160 kilonewton at the intersection, how it stretches the element to the left. So this is how this body behave under the 160 kilonewton applied force. So I'm going to end this. So this is the deformation color plot diagram. The area force, we see two color display. The red denoting 960,000 Newton and the blue denoting 640,000 Newton. You can use the probe button to show this result. I want to uncheck the snap button. I see this is this is 64,000 Newton. The blue denotes 64,000 Newton. The red denotes 96,000 Newton. So to determine the stress, you just need to divide this force by the cross-sectional area. So 64,000 Newton divided by the cross-sectional area of this material. The cross-sectional area of this material is 50 mm square. So 64,000 divided by 50 will give us the stress in this material. And for this second material, 96,000 divided by 100, which is the cross-sectional area, will give us the stress in this material. So the area force here is 64,000 Newton. Here is 96,000 Newton. I can show you this in our hand calculation. We got R1 to be 64 kilonewton, which is 64,000 Newton. And we got R3, which is the area force acting on material 2 to be 96 kilonewton, which is our 96 Newton. So once we divide by the cross-sectional area, we get 1,280 megapascal for material 1, and we get 960 megapascal for material 2. The force reaction, for the force reaction, we see the force reaction at node 1 pointing to the right, and we see the value of this reaction in this table here as 64,000 Newton in the x direction. And for the second force reaction at node 3, also pointing to the right at node 3, we see the value to be equal to 96,000 Newton. So this is how you analyze this structural problem on the ANSYS program. Now we have come to the end of this video tutorial on finite element procedure. In my next lesson, I'm going to solve this problem on the MATLAB working environment, and I'm also going to solve this problem by hand calculation. This problem is different from the problem we've solved so far. At node B, we have a gap problem 1.2 mm. So I'm going to explain how we go about analyzing this one-dimensional problem in my next video tutorial. Thank you so much for watching my video. See you soon in my next video tutorial. Thank you.